Okay, good. Okay, so I'm going to talk about three things today. The first is an alternative approach to formal mathematics, an alternative to how people normally think about formal mathematics. Then I'm going to talk a bit about an implementation of this alternative approach that I'm working on, and then I'll make some final remarks. So we'll start with this first part. And as a preface, I would say many of you have this great goal in mind of changing how mathematics is done, changing it into a formal discipline. Everyone can participate in this. I'm sure many of you support that idea. I would say I have supported that idea for many decades, but I've come to the realization that maybe this isn't working out the way we had hoped. It is not a formal discipline for the vast majority of people. So that's my preface. So I want to start with some things in the very beginning. What is formal logic? For me, formal logic is, as I've defined, you have a family of formal languages. These languages have a common formal syntax and semantics. And very importantly, you have a precise notion of logical consequence. And then, of course, you usually have a formal proof system. Now, so this brings us to what is formal mathematics. To me, formal mathematics is pretty simple. It's just doing mathematics within a formal logic. So the way you do this is you develop a formal mathematical theory, which I would say is you have a formal logic in your formal language in your logic, and you have a set of axioms, and then you can make formal statements, and then you can try to decide if those formal statements are true on the basis of your notion of logical consequence. So that's what formal mathematics is. And what are the benefits? Well, you all know what these benefits are. First of all, you can do mathematics with greater rigor because you're using a formal theory to work in. Your statements have a precise syntax and semantics. You know what they mean, and you have a precise notion of logical consequence. You know really precisely what you're trying to do. And then, because you're doing things with formal languages, you can use software in all kinds of ways to support you, and in particular, you can mechanically check your results. And very importantly, you can build up a body of mathematical knowledge as a formal structure. And you can use this structure to record this knowledge, you can analyze it, you can search it. So you have these great benefits. And when we think of people who use mathematics, maybe too often we think of mathematicians, but there's millions of people who use mathematics. And in particular, there's computing people, there's engineers. These people need formal mathematics today. Engineers need a way to precisely specify systems that they're looking at. So we have these benefits, and we have a standard approach, which, as I've described here, it emphasizes certification. So the idea with the standard approach is that you use a proof assistant, you do your mathematics with the proof assistant, and you check all details and you mechanically verify them. So that's the standard approach, and of course this gives you extremely high assurance that your results are correct. It doesn't give you 100% assurance because, of course, you could always make statements that you think capture the theorem you're trying to prove, but they're not quite right. And this approach is what I'm calling the standard approach, which I believe probably most of you either use or you're interested in. It goes back to De Bruyne in the late 1960s. So this is an old approach. And in the 90s, there was a QED manifesto, which basically called for, let's just try to formalize all basic mathematics. So this approach has been around for quite a while, and many people would say it's been a really big success. We have lots of really good proof assistants. There have been many, many theories that have been formalized. Many important theorems have been formalized. And we have a whole new area that's been around for 20 years or so called formal methods, which is using these techniques in computing mostly to deal with complex systems. And finally, we have mathematicians now, like the previous talk, was an illustration where mathematicians are thinking about using this standard approach to formalize the theorems that they're proving. So the big question is, why do we need an alternative approach? The simple reason is that this standard approach, I think, has had very little impact on mathematical practice. When I'm thinking of mathematical practice as a practice of doing mathematics, whether or not you're a mathematician. So most people do mathematics the way it's been done for, a long time, decades. They use lots of software, but they use computer algebra systems, programming languages. They're not using proof assistance. And so I would claim, if you look at all the millions of people who do mathematics, and if you include people who learn mathematics, it's billions of people, just a very, very small portion of those ever have used a formal logic or a proof system in their work. So why is this? Probably the first reason is using a proof assistant is a lot different than standard mathematical practice. It's just not the same way people do mathematics. Another thing is I will claim that most mathematics practitioners, and I'm including mathematicians, engineers, scientists, computer scientists, most of these people, they're much more interested in communication than certification. For instance, an engineer who wants to write a precise specification of some system they're interested in, they want to communicate what that system is, foremost. They're not worried about checking every detail. They're really worried about communication. So I think communication is, for most mathematics practitioners, it's more important. It's not that they're not interested in certification, they just aren't interested in going through all the effort of certifying things in a formal way. And finally, proof assistants are hard for most people to learn. You can't just run up and start doing things in a day or two. It takes a long time to become proficient. So I think there needs to be an alternative approach to get more people using formal mathematics. So what should the goal of this alternative approach be? First and foremost, it should help get the same benefits that I mentioned before, these 4 benefits of formal mathematics. Second, it should stay as close to mathematical practice as possible. And third, it should focus first on communicating, second on certifying. And last, it should enable formal mathematics to be supported by software, but software that is much easier to use than the typical proof assistant. Now, these goals are competing goals, which means it's really not possible to meet all of these goals simultaneously. I would claim if it were possible, we'd already have approaches like this. So I have a proposal for an alternative approach, and it basically has 4 parts. The first is to use an underlying logic that's designed to be as close as possible to mathematical practice. So still be a formal logic, but try to do things in a way that most people who do use mathematics would be comfortable with. The second is proofs are all written in a traditional normal style. They don't have to be formal. And the third is mathematical knowledge is organized according to the little theories approach, which I think is the best way to build up bodies of mathematical knowledge. I'll say more about that in a moment. And finally, software should be unencumbered by the need to do formal proofs. If you take a proof assistant, whatever it's doing, and you say, well, we don't have to worry about formal proofs anymore, you can easily imagine the system is going to be simpler to design and implement and use. So this approach basically calls for doing everything formally except for the proofs. Okay, so here are the design goals I have for the logic. The first thing is to base the logic on Church's type theory. And I'm sure you're familiar with Church's type theory. It provides basic machinery for predicate logic, has simple types. lambda notation, definite description, and very usefully, it has two kinds of semantics. The general model semantics, which is good for understanding the notion of logical consequence in the system, and it has the standard model semantics, which corresponds really how mathematicians think about things. So you take that and add to it support for partial functions and undefined expressions, pairs and tuples, and subtypes. All of these things I think are crucial for doing formal mathematics. And then have two kinds of syntax, sort of the official syntax, the formal syntax that software manipulate, and compact syntax, which corresponds to how people really would like to express things. And an important thing that logic needs to do is be able to support reasoning about mathematical structures. Some people would argue that mathematics is nothing more than the discovery and analysis of the studying of mathematical structures. So it should support the little theories method, and finally, of course, it should have a formal proof system. A formal proof system is almost essential, even if you're not using it for formal proofs. So what role do proofs take? Well, everything is written in a traditional style. This means that you can construct proofs much easier, and they're going to be much better for communication in general than formal proofs. So certification is still important, but the certification is done in the traditional way. You prove things with formal proofs, and you use cross-checks. Now, people don't emphasize cross-checks enough, but they're very important. When someone in mathematics proves something, and you show that proof to your friend, it's very unlikely they're going to believe your theorem just from your proof. They're going to do their own cross-checks to see if how it connects to everything else they know. So you're not relying on just traditional proof, you also have cross-checks. And it's important to realize that often traditional proofs, they describe how to build a formal proof. So that's not a formal proof, but it can be very useful just to be able to say, in your proof, this is how we would construct our formal proof. So let me talk a moment about the little theories method. So the little theories method is a really good way of building up bodies of mathematical knowledge. And the idea is your mathematical knowledge will be represented by a theory graph, a graph that has nodes and edges. These are actually directed edges. And the nodes are axiomatic theories. The edges are theory morphisms. So these are translations of the language of one theory to another. And this translation is theorem preserving in the sense that theorems are always mapped to theorems. So with these theory morphisms, you have a way of proving something in one theory and then transporting that result to another theory. Because remember, theorems are mapped to theorems. And usually you have these theoremorphisms from an abstract theory to something that's less abstract, or sometimes something that's equally as abstract. So with the little theories method, you basically develop one of these theory graphs, but you develop in the following way. Whenever you're coming up with a notion that you want to study, you develop that in the most appropriate little theory. The little theory that has exactly the right level of abstraction that you want, exactly the right vocabulary you want. And so you developed it in that, and then you use these results in other theories by creating theory morphisms for other theories. So for instance, you could develop results about monoids or groups, and then you could have theory morphisms, let's say, to the real numbers in various ways. You get several theory morphisms. And then you could transport basic results about, let's say, groups to your theory of the real numbers. And there's no reason to reprove these theorems in the real numbers. You do all the results in your theory of groups or theory of monoids. And so the power of this comes from you can take the definitions and theorems in one theory and you can move those, transport those to other theories. So this is really sort of unlocks the power of the axiomatic method. And one benefit of this is that you get an extremely strong formal polymorphism. So if you have some concept and you prove a fact about this concept in a theory, now you can use that in any other theory as long as that theory has the same structure that you're starting with, as long as you can create a theory morphism from your theory where you developed the idea to some other theory. So this has, like I said, a strong formal polymorphism, and one of the benefits, which I will have tried to exploit, is now your logic doesn't have to be polymorphic. If you're doing things with the little theories method, the logic isn't polymorphic, but you have polymorphism. And another issue that comes up is that when you create one of these theory morphisms, you're going to interpret what all the types are, what all the constants are, and so forth. If you have a base type, you might want to interpret it by another type in another theory, but you might want to interpret it by a subtype. And when you do that, this naturally leads to partial functions. So remember, in my design goals for the logic, we need to have support for partial functions. And I would just claim that this is a really valuable approach. Being able to deal with partial functions and undefined directly has many benefits. Okay, so that's the little theories method. Of course, you could have support for this with software, but there's levels of support. At the lowest level, you can just have LaTeX macros and environments. And you may say, well, what can you get done with that? Well, you can get a lot done because you don't need support for formal proofs. As probably you know, it's virtually impossible to develop formal proofs unless they're very trivial without software support. But if you don't have formal proofs, you can still take this approach and you can have very minimal software support. So you can start with just macros and environments. You could create a grammar for your language and have various tools, parsing tools, and so forth. You could go farther and have an interactive development environment. Then you could even go farther and have support, as I say here, for one of the 5 aspects of the tetrapod model of mathematical knowledge. So this is a model of how you can think about mathematical knowledge. And one of the key observations about this is if you look at software systems, they usually only support one of these aspects strongly, maybe support a couple other ones. So if you think of proof assistance, they support inference and narration maybe. They're not so good on computation. They might not be so good at concretization. Concretization is where you gather data, you gather models, you compare them, and so forth. And finally, the greatest level would be you have a complete interactive mathematical laboratory where you have all this support put together. So you can have levels of software support, and I want to emphasize that this is not a replacement for the standard approach. We're always going to need the standard approach because there's going to be cases where correctness is absolutely critical. It's critical that we know that things are correct. And when mathematics is new, we don't have a lot of intuition about it. It's critical that we can really make sure our results are correct. And finally, there can be systems that are very complex or they're just poorly understood and we don't have a strong intuition or a strong set of mathematical facts to guide us. So we need the standard approach there. So this alternative approach, I see it as a complement to the standard approach. It works along with the standard approach, but more people could use this approach than could probably use the standard approach because the barriers to using it would be lower. And the alternative approach can also be used as a stepping stone. People can try this approach, and if they like using formal mathematics, they could go further and use the standard approach. Now, this is also not formal mathematics like. Mathematical topics are formalized as formal theories. All mathematical results are proved. Now, how you prove that depends on the result. Some proofs, things are pretty obvious, could be pretty short, but everything is proved like you would do in normal, rigorous mathematics. And still, mathematics can be done with the aid of software, and we can develop bodies of mathematical knowledge as formal mathematical structures. Okay, so that ends my overview of this alternative approach. Now I'm going to talk just a little bit about an implementation for this alternative approach. And so here are the components. The first component is a logic which I call Alonzo, which is named in honor of Alonzo Church. And so I claim that this logic fulfills all the goals I had mentioned earlier for my logic. There's a notational system where you can express formal statements and formal expressions in a whole variety of notation that's very close to how you may actually want to say it. And there's a module system that supports the little theories method. So you can build theories and theory developments. A theory development is basically taking a theory and adding to it definitions and theorems. So it's extending the theory in this particular way. And we can have theory and theory developed morphisms, and we can transport definitions and theorems between theories. There's a set of latex macros and environments for presenting Alonzo type expressions and modules. Modules are these things that we use to build up theory graphs. And all of this, when I started developing this approach, I realized that if I'm actually going to get people to use it, they need a lot of instruction. So I wrote a textbook that basically presents Alonzo. It's called Simple Type Theory. And here's an overview of Alonzo. Remember, it satisfies all those goals I said, but it's based on Church's type theory. But it has an extensive set of notational definitions and conventions, so we can express things in a normal way. It admits undefined expressions according to what I call the traditional approach to undefining this. So many mathematicians, when they actually try to care about what's going on with undefined, they take this approach. My favorite example of this is Spivak's calculus book. If you look at Spivak's calculus book, he follows the approach I advocate pretty much exactly, but he doesn't ever tell the reader that he's doing this. And a good example is he uses two kinds of equality. One equality says that A equals B means A and B are defined, they equal each other. The other kind, which I call quasi-equality, A is quasi-equal to B if A equals B, or if A is undefined, B is undefined. So he uses both of these in his book. He never tells the reader he's using those. And there's one place in the book where he says, when you see equality, it depends on the context. And he points out these two. Now, there are subtypes which are represented as quasi-types. I call them quasi-types, but they're really just unary predicates. So you can represent subtypes as unary predicates, and what makes it work is that you have all this notation that makes these unary predicates look just like types. So that's why they're called quasi-types. And we have, as I sort of mentioned before, standard semantics for math, general semantics for logic. And if you take a mathematical structure, which you can define using base domains and distinguished values, then the base domains correspond in logic to base types, and the distinguished values correspond to constants. And a language in the logic is basically just a set of base types and constants. And it's equipped with theories and theory morphisms, and it has what I would say a very simple and elegant proof system based on Peter Andrews' proof system for his Q0 version of Church's type theory. The reason the system is simple and elegant is because it's based on Peter Andrews' system. Peter Andrews' system is simple and elegant, and I've basically derived the benefits from him. So, let's see. I guess I have plenty of time here. So I'll say a little bit, Alonzo, just to give you a sense of what it's like. So there are types, and what's in red is really the formal syntax. So there's just four kinds of types. There's the Boolean type, There are base types, you can have any number of those, function types and product types. So I'm not trying to present the logic at this moment, just give you a flavor of what it's like. And there are expressions, there's just 7 kinds of expressions, variables, where you have a name that has a type, constants which have a name and a type, equalities, function applications, function abstractions, definite description, and ordered pairs. And notice there are no logical constants. So you can think of these things in red, the beginning parts, you can think of these expression constructors. Those are the only logical constants. So that's what expressions are. And then I mentioned I have this compact notation. There's a whole bunch of it. So this is a compact notation in the first box. That's a notation for types. This is a notation for expressions. So it's pretty standard notation. And there's also notation for Boolean operators. I'm not going to go into all of these, but we have a whole variety of notation for Boolean operators. So in some cases, it's just abbreviations. Like when I write if there, that just stands for this. And this basically says the unique x. And if A is true, that unique x would be the value B. Otherwise, it's a value C. And if there is no unique x, it's undefined. So one of the great benefits of definite description is not only does it come up all the time, but if you have undefined expressions, then it works very nicely. If there aren't unique objects that satisfy your predicates, then your definite descriptions are just undefined. Okay, so here's the notational definitions for quantifiers. Here's some notational definitions for definedness operators. Well, if you look at the delta example, that's just for the empty function from the type alpha to beta. And if you look at A down arrow, that just means that A is defined. So I just want to give you a little sense of what this compact notation looks like. And I thought of giving some examples of showing how you'd actually express, something in mathematics, something you all know about, which are some things from calculus. So the first thing here is a limit operator. It takes a function and a value, and it gives you back the limit of this function as x goes to a. And this limit value is given by a definite description. As you know, limits don't always exist. So it's basically going to be the unique b such that this is satisfied, and this is a constant, standard delta epsilon definition. And I think you can see that the whole thing is pretty much straightforward. There's no surprises there. And notice there's no real mention of undefinedness. It's built into this description operator. If you look at the second example, this is a definition of continuous at a point. I have a function and a point, and if this is true, my function is continuous at that point. And notice there again, there's no mention about definedness, but it's actually built in because this statement says 3 things. It says that the limit of f of x as x goes to a is defined. It says f is defined in a, and it says those 2 values are equal. And then the third example is the fundamental theorem of calculus, which I won't go through this, but the key thing here is we define a function g, which is a function under the curve under the graph of f from a to x. And one question is, well, is this function defined? Is its derivative defined? And basically the conclusion says the derivative of x is defined. And not only is it defined, it equals the value of f of x. So again, I think you can see that we can express things in a fairly natural way. And define this. We don't have to explicitly mention this. Yes?
You mentioned earlier that there were 2 kinds of equality in this approach to undefinedness, and that Spivak was like equating the two in some way?
Yes.
Are you also doing that, or?
No. These are, all the equalities here are the normal quantities, which means two values are equal precisely if they're equal. The other kind was two values are equal if they're equal or if they're both undefined. I don't think, no, it doesn't come up here, but it does come up. If you're taking this approach, you're forced into these kind of two equalities. Okay, so let me have a few final remarks. So we talked a little bit about the related work. The most important related work is a proof assistant called IMPS that I worked on when I was at the MITRE Corporation many decades ago. So you can sort of tell how old I am. So this proof assistant had three innovations, I think. The first is it supported proofs with a whole variety of different kinds of computation. Many proof assistants use these approaches now. The second thing is the logic is a lot like the logic Alonzo. It admits undefined expressions, but it's actually more complicated than Alonzo. Alonzo is really a simpler version of this. And mathematical knowledge is organized using the little theories approach. I think that's all I will say since I don't have that much more time. Of course, there's other related approach. There's Tom Hale's formal abstracts approach. There's Michael Kohlhaas's flexiformal mathematics. The formal abstracts approach is you try to develop formal mathematics, but you don't necessarily prove things formally, but at least you state the theorems formally. And Michael Kohlhaas's flexiformal mathematics approach, there you can do some parts formally, some parts informally. So how does this approach differ from those? Both of those approaches sort of depend on proof assistance in some way. The approach I advocate doesn't depend on proof assistance at all. And then, of course, there's proof assistance based on Church's type theory. There's proof assistance and logical frameworks which use theory graphs. And there's software specification and development systems that use theory graphs as well. And so, here's my conclusion. I think this alternative approach can make mathematics, formal mathematics, useful, accessible, and natural to a wider range of mathematics practitioners. This approach can be used as a stepping stone to get more people using the standard approach. I think Alonzo is a good logical basis for this approach. And this approach is also well suited for developing libraries of mathematical knowledge using the little theories method, even with very minimal software support, even with just LaTeX macros and environments. And I've listed here a paper that shows how to do this with monoid theory. Here's the development graph. You don't need to understand, but there's a lot of different little theories that you develop for monoid theory, but there's not, even for something as simple as monoid theory. Here are the most important references, and thank you very much.